Conjoint analysis or stated preference analysis is a statistical technique that originated in mathematical psychology. Today it is used in many of the social science and applied science, including marketing, product management, and operations research. Let's assume you go to a shop to buy a smartphone or MP3 player. Now the salesperson tells you you can either get the model with 32 GB off the shelf, or you get a model with 64 GB, but then you have to wait 1 week for the delivery. Now the question is, what is your preference? Your preference for one of the alternatives will reveal the part-worth utilities of individual attributes. In our example, attribute 1 is the memory size and attribute 2 the delivery time. When you choose model A, it will show that you put higher emphasis on a short delivery time. Choosing model B will reveal your higher emphasis on a large memory size. So in a conjoint analysis, the part-worth utilities of individual attributes, in our case memory size and delivery time, are calculated based on the selection or ranking of a defined set of combinations of attribute values. Let's make our example a little more complex. We take into consideration 3 attributes. We look at color, green or red. We look at memory size, 16 or 64 megabyte. And we look at delivery time, 1 day or 1 week. Combining all attributes with their individual values will result in 8 different combinations. In order to solve this problem with the mathematical method, we code the values or levels with -1 and +1 each. So for example, green is coded as -1 and red is coded as +1. Here is the list of combinations with their coding. We call it the design matrix. For k attributes, there are 2 to the power of k possible combinations. Using all possible combinations is called a full factorial design. We treat the 3 attributes as variables, each of them with a value of -1 or +1. In a graphical illustration, each combination is represented as a point in a corner of a cube. One dimension of the cube shows the color, the second shows the memory size, and the third the delivery time. The next step in a conjoint analysis is to ask a person for a ranking of the possible combinations. For example, to give a 1 for the most preferred combination, going down to 8 for the least preferred combination. Then we use a simple linear model function to describe the ranking and to find the part-worth utilities. The ranking is expressed as part-worth of attribute 1, color, multiplied by the level for attribute 1, -1 or +1. Plus the part-worth of attribute 2 multiplied by the level for attribute 2 plus part-worth of attribute 3 multiplied by level for attribute 3 plus a constant. As a mathematical equation it's shown here, where beta are the part-worth utilities. Now we can set up a system of linear equations using the coded combinations and the ranking for each combination given by the person. This system of linear equations can be solved with a multivariate linear regression. Excel is a possibility to handle the case. For our simple example, here we calculate the part-worth utilities in the following way. To find the main effect for attribute 1, color, we take the average ranking for all model combinations with x1 equals +1, that means red color, and subtract the average ranking for all combinations with x1 equals -1, that means green color. In our cube, it corresponds to the sum of ranking values for all points on the right side of the vertical plane minus the sum of ranking values for all points on the left side of the vertical plane. We divide by 4 as we take the average of 4 points each and set it in relation to the total variation of the x value from -1 to +1, so we divide by 2. As a result, we get a part worth utility for color of -0.5. In the same way, we proceed for the other two dimensions. As a result, we get the wanted part worth utilities for color, memory, and delivery. The ranking calculated with the model function fits exactly the actual ranking. To calculate the relative preference for each individual attribute, we have to look at the total range of variations for our level x equal -1 and +1, which is 7 in our example. So for the attribute color, we get a relative preference of 1/7 or 14%, for memory 4/7 or 57%, and for delivery 2/7 or 29%. Now let us compare the conjunct analysis with the analytic hierarchy process AHP. The attributes in conjoint analysis correspond to the criteria or subcriteria which are compared in AHP. Instead of calculating part worth utilities, in AHP we calculate the principal eigenvector to find the relative weights. In conjoint analysis, we code attribute values as levels. In AHP, we use a ratio scale. The ranking corresponds to the evaluation of alternatives. Now, in a conjoint analysis with a full factorial design, 2 to the power of k combinations have to be ranked. In AHP, we need only k square minus k over 2 pairwise comparisons. For example, with 4 attributes or criteria, there are 16 combinations to be ranked in conjoint analysis, but only 6 pairwise comparisons in AHP. So the question is, can we reduce the number of combinations to be ranked in a conjunct analysis? Yes, we can use a so-called fractional factorial design. Instead of all 8 combinations in our example, we select half. Fractional designs have a notation as shown here. So finding the part worth utilities, we use only 2 of the 4 combinations to build the average in each dimension, and we come to the same result as for the full factorial design. Using a fractional design, we can reduce the number of combinations. As you have seen in this presentation, a simple conjoint analysis can be done with linear regression, but more complex statistical models and solutions are available.